Meet the aristocratic 16-year-old daughter of one of King Louis XIV's courtiers, Émilie du Châtelet.
Quickly! Father's coming.
Émilie du Châtelet would have a huge effect on physics in her tragically short lifetime. Unheard of for a woman of her time, she would publish many scientific works, including a translation of Sir Isaac Newton's Principia, the greatest treatise on motion ever written. Du Châtelet's translation is still the standard text in France today.
Musa mihi causas memora.
Muse my memory code.
O Muse, the causes and the crimes relate. What goddess was provoked, and whence her hate? For what offense the Queen of Heaven began to persecute so brave, so just a man?
Do not be cross with your sister, because she persecutes many a just man. Only the other night, Emily silenced the Duc de Luynes when she divided a ridiculously long number in her head in a matter of seconds. You should have seen the incredulity on their faces when they realized Emily was correct.
Was it my sister's astounding intelligence or her boundless beauty that made their mouths gape, I wonder?
Oh, well, yes. You have a point, monsieur.
Monsieur, I thank you for your kindness. I fear, however, that my wit is only a curiosity to others. If only my mind were permitted opportunity.
My dearest Emily, you are blessed with intellect and courage. Use them both, and the world will fall at your feet.
No.
In one sense, she is a woman utterly out of her true time and place. She's a philosopher, a scientist, a mathematician, a linguist. She demands a freedom that women didn't begin to enjoy until over 150 years later. A freedom to study science, to write about it, and to be published.
Du Châtelet married a general in the French army at age 19 and had 3 children. She ran a busy household, all the while pursuing her passion for science. She was 23 when she discovered advanced mathematics. She enthusiastically took lessons from one of the greatest mathematicians of the day, Pierre de Maupertuis. He was an expert on Newton, and she was his eager young student. It seems they had a brief affair. But then he set off on a polar expedition. Du Châtelet then fell passionately in love with Voltaire, France's greatest poet. A fierce critic of the king and the Catholic Church, Voltaire had been imprisoned twice and exiled to England, where he became enthralled by the ideas of Newton. Back in France, it wasn't long before he again insulted the king. Du Châtelet hid him in her country home.
The poor little creature is devoted to him.
Isolated far from Paris, Du Châtelet and Voltaire turned her chateau into a palace of learning and culture, complete with its own tiny theater, and all with the apparent blessing of her husband.
Who is the
There's a great deal of myth surrounding Du Châtelet and her love life, and most of it is very exaggerated. But her husband did accept Voltaire into his household, and he often went to Paris on behalf of Voltaire. He went to his publisher to plead Voltaire's case, to keep Voltaire out of jail. And it is also true that Émilie du Châtelet did have several affairs of a fleeting nature.
Bravo, bravo!
She created an institution to rival that of France's Royal Academy of Sciences. Many of the great philosophers, poets, and scientists of the day visited.
Oh, monsieur, you are young. I hope that soon you will judge me for my own merits, or lack of them. But do not look upon me as an appendage to this great general, or that renowned scholar. I am in my own right a whole person, responsible to myself alone for all that I am, all that I say, all that I do.
Du Châtelet learned from the brilliant men around her, but she quickly developed ideas of her own. Much to the horror of her mentors, she even dared to suspect that there was a flaw in the great Sir Isaac Newton's thinking. Newton stated that the energy of an object, the force with which it collided with another object, could very simply be accounted for by its mass times its velocity. In correspondence with scientists in Germany, Du Châtelet learned of another view, that of Gottfried Leibniz. He proposed that moving objects had a kind of inner spirit. He called it vis viva, Latin for living force. Many discounted his ideas, but Leibniz was convinced that the energy of an object was made up of its mass times its velocity squared.
Taking the square of something is an ancient procedure. If you say a garden is 4 square, you mean that it might be built up by 4 slabs along one edge and 4 along the other. So the total number of paving slabs is 4 times 4, 16. If the garden is 8 square, 8 by 8, well, 8 squared is 64. It'll have 64 slabs in it. This huge multiplication, this building up by squares, is something you find in nature all the time.
Emily, you are being absurd. Why ascribe to an object a vague and immeasurable force like vis viva? It is a return to the old ways. It is the occult.
When movement commences, you said it is true that a force is produced which did not exist until now. Think of our bodies. To have free will, we must be free to initiate motion. So all Leibniz is asking is, where does all this force come from?
In your case, my dear, the force, I am sure, is primeval.
Oh, you're infuriating. You hide behind wit and sarcasm. You only think you understand Newton. You're incapable of understanding Leibniz. You're provocateur. Everything you do is about something else and makes trouble for you. Criticize this, denounce that. Are you capable of discovering something of your own?
I discovered you!
Despite the overwhelming support for Newton, Du Châtelet did not waver in her belief. Eventually, she came across an experiment performed by a Dutch scientist, Willem Schravesond, that would prove her point.
Schravesond in Leiden has been dropping lead balls into a pan of clay.
Dropping lead balls into clay. How very imaginative.
Using Newton's formulas, Monsieur Voltaire, he then drops a second ball from a higher height, calculated to exactly double the speed of the first ball on impact. So, monsieur, care for a little wager? Newton tells us that by doubling the speed of the ball, we will double the distance it travels into the clay. Leibniz asks us to square that speed. If he is correct, the ball will travel not 2, but 4 times as far. So, who is correct?
Monsieur, I feel Mr. Newton's reputation dwindling ever so slightly.
Oh, mon père, do not succumb to her. There is no earthly reason to ascribe hidden forces to this Dutchman's lead balls.
Well, the ball travels 4 times further.
Turns out, Leibniz is the one who was right. It's the best way to express the energy of a moving object. If you drive a car at 20 miles an hour, it takes a certain distance to stop if you slam on the brakes. If you're going 3 times as fast, you're going 60 miles an hour, it won't take you 3 times as long to stop. It'll take you 9 times as long to stop.
Oh, well, it does seem worth consideration.
Perhaps we might look over his calculations.
I have already checked his figures. I am sure Leibniz is correct on this point. I intend to include a section on this matter in my book.
Really? Do be careful, madame. Do you think the Academy is ready for such an opinion?
Quite. We really should be careful.
We? I see no reason to delay. There is no right time for the truth.
Emily du Châtelet published her Institutions of Physics in 1740, and it provoked great controversy. Voltaire wrote that She was a great man whose only fault was being a woman. In her day, that was a great compliment.
I am with child.
You are sure?
Undoubtedly. 2 to 3 months. I'm afraid that
You are afraid? You should... Well, this child is obviously not mine. Nor is it your husband's. Oh, Emily, Emily.
Emily du Châtelet knew that in the 18th century, for a woman to become pregnant at the age of 43 was really very dangerous. And all the while she was pregnant, she had terrible premonitions about what was going to happen.
All her life, du Châtelet had tried to rise above the limitations placed on her gender. In the end, it was an affair with a young soldier that led to her demise. 6 days after giving birth to her 4th child, she suffered an embolism and died. Emily du Châtelet's conviction that the energy of an object is a function of the square of its speed sparked a fierce debate. After her death, it took 100 years for the idea to be accepted. Just in time for Einstein to use this brilliant insight to finally bring energy and mass together with light. Einstein pursued light right through university and beyond. Unfortunately, he'd upset so many professors that no one would write him a reference. He accepted a low-paying job in the Swiss patent office. He and Mileva married and had a child. The young family struggled, but none of it seems to bother Albert.
Einstein, I see you are busy, as usual. Look, Einstein. You have shown some quite good achievements, but listen, about your promotion. I really think it would be better to wait until you have become more fully familiar with mechanical engineering. I'm sorry. Perhaps next time.
But I wanted to hire a maid so I can get back and finish my degree. Now I will never pass my dissertation.
Oh, come, my pretty little duck. All will be fine. You'll see.
How will it be fine, Albert? Do I have to just wait another year until you are promoted? Come on. Oh.
All will be fine. All will be fine. You'll see.
There really is a very charming but kind of a self-centered streak to Einstein. He focuses only on his particular obsessions. If the rest of the world fits in around him, that's fine. If they can't, it doesn't bother him.
Albert, a pretty neck and your head spins.
Okay, so, We must behold and comprehend the mysterious.
Well, that kind of mysterious is going to get you into trouble.
I'll tell you what is truly mysterious. The secret of a long and happy marriage.
The mathematics are fine, if a little unconventional, but this only works for big systems. It'll fall down when you apply it to small systems.
I disagree. Oh, no. Here we go. Another grand theory by Herr Albert Einstein, a patent clock, third class.
What would happen if one applied those formulae to electromagnetic radiation?
Albert, you can't just take one bit of physics and apply it without proper regard to a completely different area.
Why not?
Albert, I know you like the grand linkages, the big theories, but wouldn't things be better all round if you just got going in some small area? Got a university post, get a decent wage, for God's sake. At least Mileva could study again. Then she'd be happy, and you'd be happy.
Ah, the vulgar struggle for survival. Food and sex. Spoken like a true bourgeois. Listen, I want to know how God created this world. I'm not interested in this or that phenomenon, in the spectrum of this or that element. I want to know his thoughts. The rest? The details.
Yes, but you can't feed your children on his thoughts, Bertie.
So it turns out Einstein was going for a walk with his very close friend, Michel Besso. They'd studied physics together and talked about physics and philosophy for years and years. They were very close. They had cornered the question of light from every possible angle.
See, this clock's over here.
As Einstein and Besso were ruminating on how much time it would take light to reach them from clocks at different distances, Einstein had a monumental insight.
Thank you. Thank you. I have completely solved the problem.
Albert! What Einstein did was completely turn the problem on its head. Other scientists had found it impossible to accept Maxwell's idea that light would always move away from you at 670 million miles an hour, even if you too were traveling really fast. But Einstein just accepted that as a fact. Light's speed never, ever changes. Then what he did was bend everything we know about the universe to fit light's fixed speed. What he discovered was that to do that, you have to slow down time.
His extraordinary insight is that time, as you approach the speed of light, time itself will slow down. It's a monumental shift in how we see the world.
The instant, the very instant when Einstein had this brilliant insight that time could slow down, well, the floodgates began to open. You see, before then, people had assumed that time was like a wristwatch on God's hand, that it beat at a steady rate throughout the universe, no matter where you were. Einstein said no, that the tick-tick-tick of this wristwatch was actually the click-click-click of electricity, turning into magnetism, turning into electricity. In other words, the steady pace of light itself.
"1905 was a miraculous year for Einstein and for physics. He had an unbelievable outpouring of creativity. It starts with his publication of a paper on how to work out the true size of atoms. 2 months later is the publication of his paper on the nature of light. That's what we'll learn of the Nobel Prize. The third paper, only a month later, is on how molecules move when heated, and that finally ends the debate on whether atoms really exist. The fourth paper is published at the end of this half-year period. In it, Einstein sets out his theory of light, time, and space. It was this theory of special relativity. That changed the way we see the world.
In Einstein's new world, the one true constant was not time or even space, but light. But Einstein's miracle year was not over. In one last great 1905 paper, he would propose an even deeper unity. As he computed all the implications of his new theory, he noticed another strange connection, this one between energy, mass, and light.
Einstein realizes that the speed of light is kind of like a cosmic speed limit. Nothing can go faster. So imagine we have a train charging along, and let's say it's getting up to the speed of light, and we're stuffing more and more energy in, trying to get it to go faster and faster. But it's still bumping up against the speed of light. So all this energy, where does it go? It has to go somewhere. Amazingly, it goes into the object's mass. From our point of view, the train actually gets heavier. The energy becomes mass. It's an incredible idea. Even Einstein is amazed by it.
Look, I think I have found a connection between energy and mass. If I am right, then energy and mass are not absolute. They are not distinct. They can be converted into one another. Energy can become mass, and mass can become energy. And not just energy equaling mass. Energy equals mass times the square of the speed of light.
Would you like me to check your mathematics?
Einstein sent his fifth great 1905 paper for publication. In 3 pages, he simply stated that energy and mass were connected by the square of the speed of light. E equals mc squared. With 4 familiar notes in the scale of nature, this patent officer had composed a totally fresh melody, the culmination of his 10-year journey into light.
Here we are for thousands of years thinking that over here is a world of objects, of matter, and over there is an entirely separate world of movement, of forces, of energy. And Einstein says, no, they're not separate. Energy can become mass, and crucially, mass can also become energy. There's a deep unity between energy, matter, and light.
E equals mc squared. That equation shows that every piece of matter in our universe has stored within it a fantastic amount of energy. The speed of light, for example, is about 300 million meters per second. You multiply that by itself, and you get 90 quadrillion. So in other words, what is matter? In some sense, matter is nothing but the condensation of vast amounts of energy. So in other words, if you could somehow unlock all the energy stored within my pen, that would erupt with a force comparable to an atomic bomb.
After Einstein's fifth great 1905 paper, physicists no longer spoke of mass or energy. They're now the same thing to us.
Probably the most miraculous year in science ends in silence. The articles are published to resounding nothing.
I think the gods are laughing at me.
Then slowly, it starts. A letter here, a letter there. For 4 years, Einstein answered each inquiry dutifully, trying to explain his difficult, complex ideas to a confused physics community.
I love the idea that life just went on as normal. Here are these universe-changing papers circling around, and the world is struggling to come to terms with them.
Einstein had a fan club of just one. Luckily, it happened to be the most important living physicist.
Einstein. Max Planck has sent someone to see you.
Max Planck?
Yes, he has sent his assistant. He's here to see you.
Max Planck encourages the world's most eminent physicists to take Einstein seriously. After 4 years of waiting, he is appointed professor of physics at Zurich University. From there, his career is meteoric. He is made professor of physics in Berlin, achieves world renown, and becomes a household name. He is the undisputed father of modern physics. But Einstein's success was the downfall of his marriage. In 1919, he divorced Mileva and married his cousin. His fame led to numerous affairs. E equals mc squared became the holy grail of science. It held out the promise of vast reserves of energy locked deep inside the atom. Einstein suspected that it would take 100 years of research to unlock it, but he hadn't banked on the Second World War and the genius of a Jewish woman in Hitler's Germany. "28-year-old Austrian Lisa Meitner was painfully shy. Despite her anxiety, the young doctor of physics arrived in Berlin determined to pursue a career in the exciting new field of radioactivity. Unfortunately, in 1907, German universities did not employ female graduates. Luckily, one man came to her aid.
Fräulein Meitner.
Yes?
Otto Hahn. I'm a researcher in the Chemistry Institute. Professor Planck suggested I...
Herr Hahn, I have read your papers on thorium and on mesothorium, and Dr. Planck suggested that
Yes, he suggested that I speak with you. I need someone to collaborate with.
I think I could really help with the physical analysis.
And the mathematics.
Yes. And the mathematics.
Studying radioactive atoms has become so much a collaboration between chemistry and physics these days.
Yes.
I'll ask Fischer for a laboratory then.
What moves us forward? Not time, not fame, or the promise of glory. People. I've lit the way for visionaries, been muse to 1,000 artists. The powerful found peace. The people I've moved have changed the world and walked the road no one else dare tread. For more than a century, I've watched and witnessed people emerge into the light of a new day. We began to move together, turning what ifs into what's next. We imagined the future and made history. Those who pursue perfection forge their own path, and this journey has just begun. Welcome to the next 100. Are you ready?
Excellent.
I'll speak to you soon.
Lisa Meitner had just taken the first step on a journey that would irrevocably change world history. For her, it would be a road marked with success and renown, but also with terror and betrayal.
At this time, not a lot was known about the atom. At first, people thought it was like a miniature solar system. There was a solid nucleus at the center, and electrons would spin around it, sort of like planets around our sun. A little later, some researchers proposed that the nucleus itself wasn't a solid chunk, but is made up of separate particles of protons and neutrons. But then, in what are called radioactive metals, things like radium and uranium, the nucleus itself seemed to be unstable, leaking out energy and particles. Perhaps this was an example of E = mc squared, the mass of a nucleus turning into energy.
Meitner and Hahn's collaboration to unlock the secrets of the atom started out on an extremely unequal footing. He was given a laboratory. She was forced to work in a wood shop.
I see you haven't set your hair on fire.
Herr Hahn?
The boss, he thinks that if he lets women into the chemistry institute, they'll set their hair on fire.
Oh, so his beard must be fireproof.
Good day, Herr Hahn. Good day.
You see, I am non-existent to this place. At least physicists recognize me for my abilities.
Yes, where would we chemists be without the steadying hand of the physicist?
It took years, but Lisa lost her shyness eventually. In 1912, she and Hahn moved to the brand new Kaiser Wilhelm Institute for Chemistry, where the status was really that of equals. Lisa became the first woman in Germany ever to have the title of professor.
Lisa, I am news. Remember the art student I told you of?
Yes, Edith.
Yes, well, I have Asked her to marry me, and she has accepted.
Oh, Dr. Han, congratulations.
Yes, well, I wanted you to be the first to know.
I'm very pleased for you. Very pleased.
Lisa Meitner was warm-hearted by nature. She had many friends, and she may have wanted to have a closer relationship with Otto, but it really does seem that physics was Lisa's first love, maybe even her passion.
The 1920s and 30s were the golden age of nuclear research. The largest known nucleus at the time was that of the uranium atom, containing 238 protons and neutrons. Meitner and Hahn were leading the race to see if even bigger nuclei could be created by adding more neutrons.
So, the atom, pretty familiar. Nucleus in the center, electrons orbiting around. The nucleus is our focus. The nucleus made up of protons and neutrons. Now, the largest nucleus that we know is that of the uranium atom. Its nucleus is a tightly packed structure of 238 protons and neutrons. The thrust of our work is to try to fire neutrons into this huge structure, and if we can get a neutron to stick in here, it will be a breakthrough.
Meitner may have been on the brink of a major discovery, but Germany in the 1930s was a dangerous place to be, even for a world-class scientist.
The U.S. endangers our institute.
When the Nazis came to power, one of the first things they did was to drive out Jewish academics from the universities. Einstein was very prominent, and for that reason, he was one of the first to go. He was hounded out of Germany in 1933. Lisa was not dismissed at that time. She was able to stay because she was Austrian. But in March 1938, Austria was annexed into Germany, and at that point, her situation became untenable.
What is it?
Frightening news.
What's happened?
Kurt Hess is going around saying that I should be got rid of.
I actually knew. I heard today I was going to speak to the treasurer of the institute before I told you. We'll speak to him tomorrow. Come on, let's get you home. It's late. We'll finish up.
The pressure on Meitner was unbearable. Hahn, who was known for his anti-Nazi views, did his best to protect her, at least initially.
I need to talk to you about Lisa.
Not now, I'm too busy.
We have to protect her.
How? What can we do? The situation is the way it is. Who knows what will happen next? She can't stay. It's just not tenable.
But she hasn't got a visa or even a valid passport. And she may soon be forbidden to leave Germany.
We can't harbor a Jew. If she stays, the regime will shut us all down.
Lisa. Pauline demands that you leave.
You can't throw her out.
Pauline says you should not come into the Institute anymore.
Well, I have to write up the thorium irradiation tomorrow, so I have to come in.
You've given up.
When it became clear that Meitner would be dismissed and probably arrested, physicists all around Europe wrote letters inviting her to conferences, giving her an excuse to leave Germany. The Nazis refused to let her go. In July of 1938, a Dutch colleague traveled to Berlin and illegally took Lisa back with him on a train to Holland. The trip was so frightening that at one point she begged to go back. Despite the great danger, she got through.
She had lost everything: her home, her position, her books, her salary, her pension, even her native language. She had been cut off from her work just at the time when she was leading the field and was on the brink of a major scientific discovery.
No matter what privations she suffered, Lisa was still thinking of physics. Amazingly, she and Han were able to collaborate by letter.
I hope, my dear Otto, that after 30 years of work together and friendship in the Institute, that at least the possibility remains that you tell me as much as you can about what is happening back there.
Lisa was invited by an old student friend to spend Christmas on the west coast of Sweden. Her nephew, Otto Robert Frisch, who was also a physicist, came to join her there.
Aunt? 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 Lisa, how are you, my dear? Merry Christmas, Aunt.
I need your help. Come on, let's go out.
But I was hoping you'd help me.
Back in Berlin, Han was getting strange results. He found no evidence to suggest that bombarding the uranium nucleus with neutrons had caused it to increase in size. In fact, his experiments seemed to be contaminated with radium, a smaller atom. He desperately needed Meitner's expert analysis. From afar, she was starting to suspect that something very different was happening in their experiment.
Han and Strassman are getting some strange results with the uranium work.
Really?
A couple of months ago, Han told me that they were finding radium amongst the uranium products. We are looking for a much bigger element, and here we're finding something much smaller. I urged Han to check again. It couldn't be radium. And now he writes to me and tells me that it's not radium, it's barium.
That's even smaller.
Exactly. Han is sure that it's another error, but I don't know anymore. It is at least possible that barium is being produced.
So Han still needs you to interpret the data.
It is my work too, you know.
Exactly.
Well, I can't be there, can I? Come on, let's walk.
Surely he's made a mistake, hasn't he? He hasn't done what you told him to.
Oh, my darling Robert, he may not be a brilliant theorist, but he's too good a chemist to get this wrong.
If you imagine a drop of water, a big drop, it's unstable, on the verge of breaking apart. It turns out that a big nucleus like uranium is just like that. Now, for 4 years, Meitner and Hahn and all other physicists had thought that if you pump more neutrons into this nucleus, it'll just get bigger and heavier. But suddenly, Meitner and Frisch, out in the midday snow, realized that this nucleus might just get so big that it would split in two.
If the nucleus is so big that it has trouble staying together, then couldn't just a little tiny jog from a neutron...
Yes, but if the nucleus did split, the two halves would fly apart with a huge amount of energy. Where's that energy going to come from?
How much energy?
Well, we worked out that the mutual repulsion between two nuclei would generate about 200 million electron volts. But something has to supply that energy.
Wait, let me do a packing friction calculation. The two nuclei are lighter than the original nucleus of the uranium by about 1/5 of a proton in mass.
What? So some mass has been lost. Einstein's E equals mc squared.
If we multiply the lost mass by the speed of light squared, we get $200 million electron volts. He split the atom.
No. You've split the atom.
It was an amazing discovery. Of course, in the laboratory, we're talking about tiny amounts of uranium and correspondingly tiny amounts of energy. But the point is that the amount of energy released was relatively large, and that it came from the mass of the uranium itself. The energy released was entirely consistent with Einstein's equation, E equals mc squared.
Meitner and Frisch published the discovery of what they called nuclear fission to great acclaim. But betrayal awaited them. Otto Hahn was under pressure from the Nazi regime to write his Jewish colleague out of the story. He alone was awarded the 1944 Nobel Prize for the discovery. In his speech, he barely mentioned the leading role of Meitner. Bizarrely, even after the war, Hahn maintained it was he, and not Meitner, who had discovered nuclear fission.
Now I want to write something personal, which disturbs me and which I ask you to read with more than 40-year friendship in mind and with the desire to understand me. I am now referred to as Hahn's longtime co-worker. How would you feel if you were only characterized as the longtime co-worker of me? After the last 15 years, which I wouldn't wish on any good friend, shall my scientific past also be taken from me? Is that fair? And why is it happening?
Lisa Meitner had been working on this for 30 years. She'd only broken apart a handful of atoms, but that was enough. Once she had broken even one, the genie was out of the bottle. What Meitner had started, after that, physicists around the world began to realize they could take it a lot further.
In 1942, an intense effort to build an atom bomb was begun. All over America, secret installations sprang up under the code name the Manhattan Project.
Meitner was asked to join the Manhattan Project, and she refused. She refused to have anything to do with the atomic bomb. But Robert Frisch was different. He was an important member of the team because he was convinced of the need to beat the Nazis in a nuclear arms race.
nuclear bomb was never used on Germany, but the atomic bombs dropped on Hiroshima and Nagasaki demonstrated the terrible destructive power of E equals mc squared. Vast amounts of energy in the form of electromagnetic radiation were released from a few pounds of uranium and plutonium. While the pure inquisitiveness of the world's most gifted scientists ironically had brought humanity a weapon of mass destruction, the equation's life has a parallel story of creation and beauty. Today, young physicists carry on Einstein's quest. Ever since its birth, E equals mc squared has been used to delve into the depths of time, to answer the biggest question of all: where did we come from? At particle accelerators, researchers propel atomic particles to the speed of light and smash them together, creating conditions like those in the Big Bang.
E equals mc squared actually tells us how the Big Bang itself happened. In the first moments of creation, the universe was this immensely dense, immensely concentrated eruption of energy. As it rushed apart and expanded, huge amounts of energy, or E, were converted into mass, or M. Pure energy became matter. It became the particles and atoms, and it eventually formed the first stars.
Our sun is a huge furnace floating in space, and it's powered by equals mc squared. Now, it turns out every second, 4 million tons of solid mass of the sun disappears, comes out as energy, not just a little bit of energy. It's enough to light up our entire solar system, make the solar system glow with heat and light.
And not only do stars emit energy in accordance with E equals mc squared, the whole process actually creates life itself. Eventually, a massive star dies, the debris floats around, clusters together, gets pulled into the orbits of another star, and becomes a planet. We humans and the Earth we stand on are made of stardust. We are a direct product of E equals mc squared.
Building on the work of scientists through the ages, new generations are searching for answers. Using bold new tools that reach almost to the speed of light, they can now ask questions that their predecessors could never have even imagined. As Einstein himself knew, the journey of discovery is sometimes painful, sometimes joyful. It is as old as human curiosity itself, and never, ever ends.